I think it's about time to start. I'm going to start anyway.
Okay.
It may not be time. I think it's, I don't know. I'm a minute late. Oh, man. Oh, goodness gracious. What's happening? I'll have to calculate faster. All right. Heavenly Father, we thank you for this day. Again, I thank you for this class and your many blessings. Help us to glorify you in what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, so I got problems to solve. Let's see here if I can find one that I like. Okay, here's one that's similar to the one we worked last time, but this time it's going to be a wee bit different. And so here we go. We're going to try to find complete power series solution centered at 0. For the differential equation y prime prime plus x squared times y is equal to 0. I am kind of curious. Hey, let me digress here for a moment. What happens if we try to Laplace transform this thing? Anyway, right? I mean, I always want to see what happens. Laplace transform, and we'll assume that the let's just, for the sake of the Laplace transform, assume that like y of 0 is 1 and y prime of 0 is 0, just to make things as simple as possible for this digression, right? So the Laplace transform of y prime prime of s, and then what happens when we have an x squared? That does what? D squared ds squared, right? The Laplace transform of y equal to 0. Okay, so this gives me s squared. Man, I hope I don't solve this real simple. That would be annoying. That would be actually really annoying, because this is one of my favorite series examples. S squared, I've never tried this before, I don't think. S squared y minus 1. Oh, well, look at that. Ew. Oh, it's mocking us, isn't it? Look at that. So, oh, look at that. Isn't that perverse? Look at this. Look, it's like d, d squared y ds squared plus s squared big Y is equal to 1. So this, like, compare that to the given differential equation. Oh, that was an s squared, right? Isn't that wacky? Like, what happened? This is the same thing, but now it's non-homogeneous. It's worse in the S domain. So obviously, okay, so I proved my point. Laplace transforms will not help us here, right? So what we're going to do is we're going to use the series solution technique, right? So we propose that y is the sum n equals 0 to infinity of, let's say, a sub n x to the power n, right? And then if we differentiate that thing 2 times, what do we get? We get the sum n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2, right? We worked this out. I guess I skipped a step, but you'll forgive me. Right. All right. So that's the second derivative. There's the function. All right. So we've got this. On the other hand, what does x squared times y look like? what happens when we multiply x squared into here? X to the what? N plus 2, right? When we multiply x squared in, x squared times x to the n gives us x to the n plus 2. All right, so what I want to do is I want to plug these into my given differential equation, right? But I also know what I'm going to do is I'm going to equate coefficients, right? I want to be able to add these sums together. So what I have to do to make them sort of summable is to make them, of the same format, right? But we got to, you guys asked me last time, well, what if they don't meet at this? What if they don't start at the same point, right? And I think we've reached that point, yeah? Because this one we can write as, a sub 0 x squared. Well, let me not write this one. I'm an idiot. This one starts at x squared, right? This one, on the other hand, starts where? It starts at constant terms, right? Right, so like this one, if I write out, I've got n equals 2. I've got 2 times 1, which is 2, 2a2, plus 3 times 2, which is 6a3 x, right? And then plus the sum, n equals what to infinity of n times n minus 1 times a sub n x to the n minus 2. Anybody? Where does that sum start?
What's the question?
Where does the sum start? This right here is n equals to 2. This right here is n equals to 3. So this guy starts at 4. Now the reason I'm doing that is now this also starts at x squared, right? See, that's where these two sums are common, right? All right, so let me try to put things together over here. So what we got, if I plug things in, I've got y prime prime plus x squared y equals to 0. So I've got these exceptional terms that I'll stick out front. 2a2, all right, plus 6a3x, all right, plus something. I'm going to do a little bit more work on this board before I go over there, though. See, because what I want to do is I want to make these two expressions match up, all right? So my suggestion is we make this one have like a, I don't know, let's say j equals n plus 2 substitution here, which means n is j minus 2, right? And this one over here, I'm going to make a j equals to n minus 2 substitution, which means n is equal to j plus 2, right? So in view of that, I have my y prime prime. Oh, fine, I'll write it out here. So that gives me 2a2 plus 6a3x plus the sum n equals, not n, oh, n equals 4 was what? J equals 2, right? So j equals 2 to infinity of n, which was j plus 2 times j plus 1 times a sub j plus 2 x to the power j. All right, I got that. This one down here, I've got some j equals 2 to infinity of like a sub j minus 2 times x to the, well, to the j. That was a little less exciting. All right, so put that in up here. So for my y prime prime, I've got this sum, and I'll write out an extra step here to make it look harder than it is. J equals 2 to infinity of j plus 2 times j plus 1 a sub j plus 2 x to the power j, and then I have plus the x squared term, x squared y term, sum j equals 2 to infinity a sub j minus 2 x to the power j. I think if I got that right. Let's see here. So, what do we got? See, now we've made these match up, right? So now we can combine the sums because they have the same type of monomial on each, right? These match. The starting point matches. So, theorem of power series, if you like, we can add these. This is all equal to what? 0, right? So we get, put it all together here, 2a2 plus 6a3x plus the sum j equals 2 to infinity, all right, of parentheses j plus 2 times j plus 1 a sub j plus 2 plus a sub j minus 2, close big old parentheses here, x to the power j. Aw, man. I tried. Anyway, so we have this equation, right? For our solution to work, we need this to work out to 0, right? So certain things are non-negotiable. Like these two outliers here are wonderful. What do these tell us? So like from the constant term, we get 2a2 equals to 0. From the x term equating coefficients, we get 6a3 is equal to 0, right? And from, what's that?
Therefore, a2 is equal to 0 and a3 is equal to 0.
Very true, yes. Granted, all right. And then, well, x to the power j, right, for j greater than or equal to 2, we have j plus 2 times j plus 1, a sub j plus 2 plus a sub j minus 2 is equal to 0. I'm not particularly fond of this formula as it's currently written. Let's make it prettier. So, opening move, I've got an a sub j plus 2 is equal to minus a sub j minus 2 divided by j plus 2 times j plus 1, right? And that's for j greater than or equal to 2. I recommend that we swap out that j plus 2 for n, right? Do you want me to use m instead? Votes for m. Votes for n. The n's have it. So a sub n, is minus a sub n minus what? If n equals j plus 2, then n minus 4 is j plus 2 minus 4, which is j minus 2, right? So we have n minus 4 here. A sub n minus 4 divided by, what did you say? N? Oh, well, the quotient, the denominator, we match the index, right? So if there's an n here, there's an n there. So we've just got n times n minus 1. All right, let me make the a bigger. You can tell that's a subscript, right? So there's like a fourplicity to this problem, right? There's an interlinking of coefficients that are linked by 4, right? Do you guys know that we can write the integers in terms of like these kinds of things, right? Like if we take, the natural numbers, well, forget the natural, integers. We can write those as like multiples of 4 plus 1, multiples of 4 plus 2, multiples of 4 plus 3. Right? You can divide the integers into these 4 classes, like 0, 4, 8, 12, so forth and so on, 1, 5, 9, 13, so on and so on, 2, 6, 10, 14, so on and so on, 3, you get the idea, right? And so basically we can look at n equals to either, like 4k, or 4k plus 1, or 4k plus 2, or 4k plus 3. This is all the cases, right? All the cases to consider. Does that make sense? Like we divided even and odd last time, right? But this time it's more natural to like think about fourplicity, if you like. Let me do, so like you guys tell me, what is a sub, a sub 4k plus 2 is equal to what? It's equal to a sub 4k plus 3. Why is this? Let me be a little bit less cryptic. Like a sub 2 is what? Put k equal to 1 for a second. A sub 6 is equal to what? Minus a sub 2 over 6 times 5, which is? Zero, right? And likewise, a sub 10 is minus a sub 6 over 10 times 9, which is 0. We could be here all day, right? These are all 0. And for almost the same reason, right? If we look at a sub, let's see, 4 plus 3, 7, is minus a sub 3 divided by 7 times 6, right? Is 0, etc. So these are all 0. So half of the story is gone right there. Those are all 0, right? But that's not everything, right? What else do we have to deal with? The other kinds of things, right? Like multiples of, we've got the 4k plus 1, and we've also got the 4k kind of things, right? So let's analyze those over here. Let's see here. So let us face the music. We've got to grapple with the formula a sub n is equal to minus a sub n minus, come on, it's still wet, n minus 4 divided by n times n minus 1, right? And so let's look at the case n equals to 4k, right? We'll put k equals to 1. We have a sub 4, right, is equal to minus a sub 0 divided by 4 times 3. What comes next? A sub what? Dr. Wang said something very interesting today. It's not entirely relevant to this class, but kinda. He said that it's been proved that like the most things you can think about at once in the human mind is like 7 plus or minus 2. So he's like, but on the other hand,
8.
for me 5, right? So for some of you maybe 9, but
Maybe 2.
but then Wang pointed out that if you draw a graph, you can easily think about more than 9 things. So that's why graphing in Calculus 3 is like super important, because it's a way of expanding your mind. So there you go. That's a helpful comment for Calc 3. somewhat relevant to you guys. I mean, for us, I don't think graphing, I guess what I'm saying in here is write out your work, right? I mean, that's kind of the closest analog. I'm not sure that that helps too much us in here. A sub 8, right, is minus a sub 4 divided by 8 times 7, which is minus 1 squared times a sub 0 over 8 times 7 times 4 times 3. K equals to a 3 is a sub 12, which by the way is minus a sub 8 divided by 12 times 11, which is equal to minus 1 cubed a sub 0 divided by 12 times 11 times 8 times 7 times 4 times 3.
-1 to the n times a sub naught to n factorial.
So you want me to write, you want me to, it's not a factorial, no. If only, but no. So we have a separated factorial. A sub 4k, I don't have a name for it, but a sub 4k is apparently minus 1 to the k, right? We see that. Minus 1 to the k, a sub naught, divided by 4k times 4k minus 1, all right? And that goes on until it gets to, 12 times 11 times 8. However much of this you can suffer writing out, I mean, hopefully enough that I can see that you're doing what you're supposed to and I can give you full credit, whatever that means. Convince me that you know what you're doing. I mean, there's probably ways of simplifying this, right? I'm going to leave it like that, though, just for the sake of the moment. Yeah.
When you put like the 4k or 4k minus 1 in power,
Oh, well, all right. Let me see if I can. So you want me to? All right, fine. So this is minus a sub 0 over 3 times 4 to the 1. This is minus 1 squared times a sub 0. How many 4s do I got? I got 1 and 8. I got 1 and 4, so I've got 4 squared. But I've got, golly, goodness gracious. Is that what I want? Is that what I want? I guess 3 times 7. I don't. If I do that, then I need, that's ugly. I get a times 2 times 4 squared, I guess. Minus 1 cubed a sub 0. If I pull out the factor of 4 here, I've got 3 times 11 times 2 times 7 times 3 times 4 to the cubed here. I don't know. What?
Question. Isn't it supposed to be, if we're doing -1 to the k power, wouldn't in the case of k equals 2 at the very beginning, it'd be positive plus a to the 4? Because when something's a negative is squared, it's positive. So that's, if it's negative, doesn't that mean our powers have to be odd, so k plus 1 power?
I mean, this is the k equals 1, I've got a minus.
Yeah.
K equals 2, I've got a minus from this, but I also got a minus from that one. They combined to give me a square.
Okay.
So, I mean, this is k equals 1,
Yes.
k equals 2,
Yes.
k.
Okay.
Because he still has a negative 1 factor. Like, yeah,
Yes.
that would be just 1, but he still counted so we can see what's happening.
Okay.
Now, I do claim in the notes that this can be rewritten. And I'm usually smarter when I wrote these notes, so we'll trust it for the moment. But I claim that this can be rewritten minus 1 to the k divided by k factorial times 4 to the power k times 4k minus 1 times 4k minus 5 on down the line until we get to 11 times 7 times 3. Of course, the a sub naught is still up there. I might be able to see that pattern. I don't know. Let me try again. I get the 3, 4k minus. Let's see here. I'm not sure about this 2 here. I'm a little bit leery of. Is that supposed to be there? What is 4? 4 is 8. 8 minus 1, 7. I think that 2. Oh, see, that 2 is supposed to fold into the, like this 2 and this 3 go into the, those go into the 3, well, no, the 3 doesn't. The 2 is the 2 factorial. All right, so I've got the 2 factorial and 7 times 3 times 4 to the squared. Like that's how that, yeah. So as we're currently experiencing, you could easily spend a lot of time trying to simplify these formulas. And that's interesting, but that's the difference between getting, 100% credit for the problem versus, 90% credit. Or if it's a particularly nefarious simplification, maybe I give you bonus points for doing it on the time test or whatever. But like this formula at the top is a perfectly good formula for a sub 4k. It's not as good as this one, right? But it's pretty good. So, all right. So that's n equals 4k. What's the other one? N equals 2, 4k plus 1, right? How's that work out? So n equals 4k plus 1, we have to, again, consider the recurrence relation a sub n is equal to minus a sub n minus 4 divided by n times n minus 1, right? By the way, think about this. If we had not rewritten our recurrence relation from the way it originally came to us, imagine if we did all of this through the lens of the formula a sub j plus 2 is equal to minus a sub j minus 2 divided by j plus 2 times j plus 1. That would have been much harder. Don't ignore that step. Like that's an important, you're making your life so much easier by simplifying the formula before you do a bunch of analysis with it. So it pays off. All right, so let us continue reaping the benefits. So this is a sub 5 for k equals to 1. A sub 5 is minus a sub 1 over 5 times 4. K equals to 2. We get a sub 9 is equal to minus a sub 5 over 9 times 8, which by the way is minus 1 squared times a sub 1 divided by 9 times 8 times 5 times 4. K equals to 3. We've got a sub, let's see, 9 plus 4 is 13. That's minus a sub 9 divided by 13 times 12, which of course gives us minus 1 cubed a sub 1 divided by 13 times 12 times 9 times 8 times 5 times 4. All right, I think I hope you can see where we're going with this. I'm going to write I'll write the formula for it up here so we can all see it. We've got a sub 4k plus 1. Apparently the pattern is minus 1 to the power k, right? A sub 1 divided by, all right, so we've just got 4k plus 1 times 4k, right? And on down the line until eventually we get to 13 times 12 times 9 times 8 times 5 times 4, right? And if we are feeling smarter than I am feeling today, then you can simplify the formula, probably, and you can factor out a k factorial and a 4 to the k from all that jazz. So there's like a k factorial, 4 to the k, and that leaves you with 4k plus 1 times 4k minus 3, and on down until eventually all that you're left with is the 13, the 9, and the 5. All right. Es bueno. So we're not done, right? Now we put all the pieces together, right? We write the general solution. What's it look like? So here we go. We have found that y is equal to a sub 0 times the sum k equals 0 to infinity. All right, minus 1 to the k. I'll use the nice formula. Divided by k factorial times 4 to the k times 4k minus 1 times 4k minus 5, dot, 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 until we get 11, 7, and 3. All right. All of that is x times x to the what power? This was a sub 4k, right? So x to the 4k. And then plus a sub 1, again, sum k equals 0 to infinity. All right. I guess I don't really need these parentheses. Let me not. All right. Minus 1 to the k divided by k factorial 4 to the power k times, what was it? 4k plus 1. 4k what? Minus 3. And on down the line until finally we get to 13, 9, and 5. I need glasses. All right, 9 and 5. That's your coefficient, and the monomial that comes with it is x to the 4k plus 1. There you go. That is the solution, the general solution to y prime prime plus x squared y equal to 0. Yep. Now, so I think the method is clear enough. It's just, you know, a little bit difficult, right? Yeah, I think. Let's see here. Let me show you guys. I'll show you guys two more of these here. If I can get this thing to work. Come on. Well. All right. Are you guys enjoying CFA? Eh. I'm starting to think about canceling class on CFA generally going forward because I'm tired of like parking halfway to the moon. Duck Dynasty? What's that? Just kidding.
And the CFA families actually pay for things. So.
Ah. I thought you guys pay for things. Is school free? Let's see here.
We pay for the school, but we don't pay for any of the, like, the extra things. People
I see.
sell things, fundraise, and we're like, oh.
Ah, all right. Giving Day. Oh, yes, of course. All right. So
Love giving.
here is another one of these problems. And I think I'm just going to talk you guys through the other ones. We've gone through two of these complete power series solutions fairly carefully, I should say, step by step, right? Like maybe next time we get back to new material, I'll do another one of these, but like just the first three terms. I'll focus more on that like next time, maybe. Because I do usually ask about finding just the first three terms. And if you just want to find the first three terms, you don't need to do all this, right? It's easier. Okay, so anyway, so here we have y prime prime plus xy prime plus 3y equal to 0. The method is the same. I propose a series, I differentiate it, twice differentiate it, and then plug it into the differential equation, all right? Now the difference here and what I've been doing in class is, I've been first reformatting these things before I add them. In the notes, I add them and then I reformat them. Maybe that's easier to follow actually. So anyway, I add them, but I can't actually add them because I've got different powers here, right? So, and then I'm simplifying. I'm like bringing the x inside and the 3 like that, all right, cleaning it up. And then what comes next is relabeling. So now I'm relabeling this one to x to the j, that one to x to the j, and they're all now into the j, making a substitution so they match up. But you notice that this one's not like the others. This one does not belong because this one starts at 1. Wait a minute, this one starts at 0. Maybe these two don't belong. So we'll have to strip off the 0th one here and the 0th one there in order to make all three of them start at power 1, right? And so that's what I do. Here's the 0th term from that one, the 0th term from that one out front. These are exceptional. And then we have that. So that gives us a recurrence relation. This time there's a tuplicity to the problem, right? Like it's linked by 2, and there's your recurrence relation, which then yep.
So the last term is c sub j and x to the j. But shouldn't it be like j plus 2 and x to the j plus 2?
Where are you talking about?
Right where your cursor is, it defines that k minus 2 is equal to j.
Dang it, where's my cursor?
And it's near the top of the paper to the left.
curse the cursor.
Under reliable.
Ah, here, what's this?
Related.
So if you're defining that k minus 2 is equal to j, shouldn't the third term of your power series,
This one?
that the third term, the one, it's like the 3 times c to the sub j?
This, no. I'm only relabeling this piece with that substitution, not all of them.
Okay.
Yeah.
That's why I was confused.
Yes. We have to make different substitutions on the different sums. Otherwise, it'd be like trying to move 3 people who are standing apart to make them stand together, but every time you shift them all the same way, then they just still stay apart, like something like that. I'm sure you could think of a better analogy. Maybe something involving ducks and dynasties or something. I don't know, but indeed. So you plug these handy-dandy formulas, and then we just look at cases and we study the pattern. Maybe things simplify, maybe things don't. Like last class, we found factorials. That was super nice, right? But the thing is, the solution doesn't have to be anything super nice. Like, I could stare at you guys all day and go, what's the name of this? And at no point are you going to be like, it's the hyperbolic caplortion or something. I mean, it's got no name. It's nameless. It's just a particular... Actually, it probably does have a name. This is well, maybe this one doesn't, but I think the one we were just looking at, those solutions are called Airy functions, because that's a famous differential equation of mathematical physics, and the solutions have names. In fact, that's typically how famous functions of mathematical physics are defined. They've got some sort of differential equation which defines them. Like I was saying last time, sine and cosine could be defined by y prime prime plus y equal to 0. There's a different differential equation which will define what are called Bessel functions. Now, that's beyond our current context. Our current context is we're solving differential equations that are what are called ordinary points. An ordinary point takes for granted the fact that the solution can be written as a power series. But in fact, as we go on and study these problems in the broader scope of how they appear, we run into what are called singular points. Singular points, you need something besides power series to solve. We've actually already run into these. If you think about the Cauchy-Euler problem, x squared y prime prime plus like x y prime plus a constant times y equals to 0, that is something that if you remember the solution sets, we had like square root of x, or we had natural log of x, we had things like that. Those actually don't have power series expansions. Well, not at 0 anyway. So anyway, I'm just saying that this is the start of a larger story. Yeah? Here's another one. This one actually is kind of more what I was talking about, first 3 terms. So here we've got, y prime prime plus 1 over 1 minus x times y prime plus e to the xy, and I give initial conditions, right? All right, so the way this is done is we expand the coefficient functions with their Maclaurin expansions. Like 1 over 1 minus x is that, right? E to the x has this Maclaurin expansion, so then I plug those in to where they are in the differential equation, right? Then I plug in the power series for y prime, and y prime prime, and I get this grand glorious equation, right? And then I simply look for constant terms, linear terms, quadratic terms, and those have to separately vanish. So I get, like, the constant terms give me this equation. The x ones give me that equation, and so forth. But we could have made this easier from the start. See, because up here, y of 0 is 0, right? That tells me, in fact, that c0 is 0. And y prime of 0 is 1. That actually tells me c1 is 1. So then I can put those into here. c0 is 0, c1 is 1. Apparently c2 is minus a half. And, so forth. So when you put those in, we get this as our solution up to order 4, right? So I ask a mix, like on the test, well, do I even have a test? On the boss fight, I guess I should say, right? I've invented a new category of assignment for you guys, the boss fight. So these problems feel like that though, right? Like I just spent 35 minutes of class to solve a single problem, right? And I was not going that slowly either, right? Yeah. Oh, come on.
The boss fights take on or in person?
I don't know.
I hope they're taken.
I think I'm ready for you to take home. Aw, the double scrolling. The double scrolling got me. Come on. All right. Now, here's another one. We're solving y prime equal to sine of x over 1 minus x squared, right? So this one, I do the, geometric series for that. This one's actually centered at 1 rather than 0, so it's a little bit different, right? And because we can. And then, come on. Let's see here. And then sine of x we can rewrite as sine of x plus 1 minus 1, like so, right? And then we use adding Engels formulas, and it gives me a sine and a cosine series centered at 1, of which here are the first few terms. Then you plug those in to the differential equation, and this one, it's y prime, right? So this one's especially stupid. I don't actually need to do this equating coefficient things, right? Because we can just integrate both sides, you see? However, I would recommend not trying to integrate sine x over 1 minus 1 times 1 minus quantity x minus 1 squared, because that would be like, I don't know how to integrate. Do you know how to integrate that? I don't know how to integrate that. I do know how to find a power series for it, though, and integrate term by term, which is what I do here. See, because this I can't integrate, but that I can integrate term by term. And so there we go. That's the solution. So sometimes we can just integrate, right? But usually we're stuck with something that's, like why couldn't we do that with this problem? Because there's a y prime prime, there's a y prime, and there's a y. I can't just isolate y prime and integrate, right? If I integrate y prime, it begs the question, what do you do with y, right? I mean, maybe the y prime integrates to y prime, but you still got, it's just, you have to isolate the derivative in order to do the integration thing. And only a precious few differential equations allow for that. All right. And that brings us to singular points, which is where I'll pick up next time we come back to this material. What happens Monday?
Review for the exam.
Review for the exam Wednesday, the test Wednesday. And you guys do what? You give me your surprise technician, what is it? Yes, if you have questions about